Okay, so the last section of Unit 5 is the making connections, like always, right? Bringing it all together, comparing it to more real life situations. And we're talking about exponential models now. So, some key ideas here before we start. Exponential functions and their derivatives are important modeling tools for a variety of fields of study, which is why you're probably taking calculus, right? If you're interested in nuclear engineering, mechanical engineering, electronics in any way, biology, and environmental science. The general form of an exponential function is, again, y equals a times b to the exponent x, where just a review from grade 11, where a is the initial value, right? B is the growth and decay factor. Well, whether it's growth, right, greater than 1 or decay between 0 and 1. So again, A cannot equal 0 in front and B cannot equal 0. So A and B cannot equal 0 and B has to be greater than 0. Okay. So we'll look at, we've got just looking ahead here, we've got one example that talks about a bacterial colony, and then we have a second example of this father being on a diet. And that's it, 2 questions. So our first question will be using an example with a base of B. So we're going to be following along with this, say exponential growth or decay, we'll see. I think it ends up being an exponential growth question. And then we will look at also number 2, an example with a base of E to look at both. So again, exponential functions in the past, right? You might have been reading things talking about half-life, if something is double its lifespan, and plugging that into the equation last year, right? So number 1, a bacterial colony has a mass that varies with time. So is it getting bigger or is it getting smaller? The original mass of the bacteria is 20 grams. So we already know that that original mass, hopefully when you're reading, just getting my pencil here, that would equal A, right? My initial value. It already says original, so that's the same thing as initial. And the mass triples each day, triples, so like times 3. So that would tell us that it's a growth question, right? It's growing every day. It's I should put exponential growth. Write an equation to model the growth of the mass of the colony. So let's write out our general equation from up above. Y equals the initial value multiplied by the growth factor. Whether you put X outside or inside the bracket, it's still just pertaining to the B, so it doesn't really matter. So therefore, our general equation would be the initial value is always going to be 20, right? Always. My growth factor is always going to be the same. My growth factor is a 3, right? It's tripling. And then we don't know what the general equation would have. X and Y remain X and Y variables. And you could use M for mass and T for time, and time is in days. So we should probably say what our, so just to say here, A is 20, right? And our B, our growth factor was 3. But I want to let X, right? I have to say what my variables are. Let X represent time in days. So we're talking about number of days here. And let Y represent the mass, right? Let Y represent the mass. In what units? It talks about grams here. So we must be talking about the mass is in grams. All right, that's it. This is basically the answer to 1A. So obviously we're going to be using that here. So what is the initial rate of change of the mass of the colony to the nearest gram per day? So we're looking at grams per day. Okay, so what is the initial? So rate of change, again, rate of change is telling us that we need a derivative. So again, I have the equation right there. You could rewrite it, but I don't see the need if it's kind of right in front of you there. So to get the derivative, if you look, I have a constant in front multiplied by a base with an exponent, and the base is B. So I'm going to be looking at the constant multiple rule if you need to go back and take a look at that. So the constant multiple rule here would be leave the constant alone, the 20, right? And then I have 3 to the power of X. So I write it out as 3 to the power of X still. But then remember when it's b to the power of x, then multiplied by the ln of b. So multiplied by the ln of 3. Multiplied by the ln of 3. And then I was going to clean it up. And I could put 20, let's say, ln 3 multiplied by 3 to the power of x. It doesn't matter. But initial is another word there. What is the initial rate of change? So initially is talking about time. Time is x when time is 0. So just sub in a value of x equals 0. So from here, I'm just going to go over here. So I have 20 times the ln of 3 multiplied by 3 to the exponent of 0, which just equals 1. So then my answer is 20 times the ln of 3, right? And then I can plug that in the calculator. Because of the way the question is, it seems like it's asking us for an exact number, right? What is the mass of the colony to the nearest gram per day? So go ahead and get a numerical value here. So that's about, to the nearest gram per day is rounding to the whole number, right? So it's about, you should get 22 from 20 multiplied by ln of 3. So the answer would be 22 grams per day. Okay. C, I'm going to need a little bit more space here. I'll go through it with you just how to start it, and then we'll clear and move up. So during which day, so talking about day 1, day 2, day 3 again, so X value in days, during which day is the mass of the colony increasing by 60 grams per day? So first of all, it's saying increasing, which you increase and decrease within the first derivative, right, chart. And 60 grams per day, that's also a rate that it's giving you too. So there's 2 different hints they're telling you that you'd be using the derivative again, the first derivative. So there's my rate. So we will use our derivative equation. So here's where I'm just going to move that up then and recopy that down. So let's copy down our derivative. Might need, we'll see if I can squeeze it in there. I might have to write a little bit smaller. So rewriting our derivative before I set it equal to 0, right? So our derivative, whoops, didn't have my pen there. My derivative before we set it equal to 0 was, well, I think I had it as 20 times ln of 3 multiplied by 3 to the power of x, right? Or it could have been 20 multiplied by 3 to the exponent x multiplied by the ln of 3, depending if you rewrote it that way or not. Same thing, right? And so because we're in a derivative and it's telling us that the mass of the colony is increasing by 60 grams a day, our mass is 60, right? Mass is 60 and mass is our y value. So we're going to plug in to our first derivative, 60 on the left-hand side where mass would be, and then 20 times the ln of 3 multiplied by 3 to the exponent x. And then we need to solve for x because during which day. My only variable here is x, during which day. X is number of days, so I need to solve for x. So how do I do that now? Take a look ahead here. Solve for x. First thing I would do is I could divide by 20 on both sides, right? Because that's just a constant in front. So again, instead of writing it out a second time, I'm just going to divide by 20 on this, divide the whole thing by 20 and just show what that cleaned up would be. So that would end up being 3 equals, did I write it backwards here? 3 equals ln of 3 multiplied by 3 to the exponent x. Or if you divided by 20 here, you'd have 3x first multiplied by ln of 3. Doesn't matter, they're multiplied by each other, whether you have this first or this first, but you should get down to this statement just depending on which term is first. So then again, I'm trying to solve for x. So how do I solve for x here? So one way is that I could take the, actually I can go one step further here. First, I can divide by the ln of 3 up on both sides, right? To at least clean it up a little bit more. So that I'm going to write over here. So 3 divided by the ln of 3 equals the ln of 3 multiplied by 3 to the power of x divided by ln of 3, gets rid of it on that side. So then I'm left with, again, 3 divided by the ln of 3 is equal to a base of 3 to the power of x. solve for x. So this is where, sorry, I was talking about that there's two different ways that I could do this. So one way is I can take the log of both sides, or I can take the ln of both sides, or actually I guess a third way could be also converting it to logarithmic form. So I'll show two of those ways and then you can kind of choose which way you would like. So yes, I do need more room. So whether, I know you guys can't move this down, but whether you want to just kind of go off to the side here, I need about this much space, about the space in D left, wherever you want to choose to fit that in. Let's see if I can I get this to move down? Come on. So that when I move this up, still be part of question C. Perfect. Okay, so I'm just going to do this in different colors to show you the different ways, and you can choose which way that you like the best. So one way is I'm going to take the ln of both sides. Okay, so take the ln of the left side, the ln of bracket 3 over ln of 3 is equal to the ln of bracket 3 to the exponent x. So then I would have the ln, nothing changes on the left side, of 3 over ln of 3 equaling, again, when I have the ln and I have an exponent, you don't want x as the exponent, right? So x would come in front, x ln 3. So then to solve for x, you would just divide by ln of 3 on both sides. So then I would end up with, it's going to look a little messy, but not bad. The ln of 3 divided by ln of 3, sorry, equals x. And then don't forget here, divided by ln of 3, and then here divided by ln of 3. I'm just going to skip the step here of dividing by ln of 3 on that side. So ln of, I'm just making sure I wrote it down right, 3 over ln of 3 divided by the ln of 3, which you should do as well before you actually plug it into the calculator, because if you had done something wrong, why waste your time getting to the calculator at that point, right? So now be careful and plug this in. Again, however you do that, 3 divided by the ln of 3, and then the ln of that number divided by the ln of 3, you should get a value of about 0.9. So when the question says during which day, it's at 0.9 days. So that's just under, like before the first day is up, right? So it's within the first day. And then I'll do my therefore statement, but I'll show you a second way of doing it as well. So the other one was, because I have this step here, this is the step when I'm like, okay, what do I need to do to solve for x? This is one way. Because I have a base of 3, right? I can change this, I said, into logarithmic form. So I have a log of base 3 of 3 over ln of 3 equaling x. And then when it's a base of 3, I can write that out as a log of 3 over ln of 3, right, divided by the log of 3 equaling x. And same thing, if you plug this into your calculator, you should get an answer of 0.9. So again, just depending on which way you'd like to do it, or the third way as well. So the answer is therefore within the first day. So within the first day, the colony increases by 60 grams per day. Then we do have a part D that we move down, right? So I think I need do I need part of D for, I just need my answer of 0.9 before I clear it here, okay? So D, what is the mass of the colony when its mass, so I'm looking for what is the mass of the colony, my Y value, when its mass is increasing by 60 grams per day to the nearest gram, right? So it's asking for the mass, so I'm using my original formula. It's not asking me to use anything. It's saying when the mass is increasing by 60 grams a day. But when the mass is increasing by 60 grams a day was question C, where I knew that the day that it was increasing by 60 grams a day, my X value was 0.9, right? It was just under a day to the nearest gram. So I'm basically just plugging in that X value of 0.9 into my original equation. So my original equation up in A, I'm just checking, was 20 multiplied by 3 to the power of X. Plug in 0.9, 20 multiplied by 3 to the exponent 0.9. Again, BEDMAS that first before you multiply by 20. Do not do 60. You might make that mistake. You should get about 50. It says to the nearest gram, so whole number. So you should get about 54 grams. So the mass of the colony on that day, when it was increasing by that, which we figured out in C, the mass would be 54 grams. Okay, so that takes care of an example and different parts of it with a base of B. Now we're going to move on to number 2, which I said, which is looking at an exponential equation with a base of E. Just to move this up. So Joe's father is on a diet. He currently, or his original mass, so I'm saying before he starts the diet, his original mass is 102 kilograms. The diet allows him to lose mass exponentially. So his mass is modeled by this equation, and they give you the equation. So W is equal to, now this is, you would say this as W naught. So W naught multiplied by a base of E to the exponent K times T, where W naught is his original mass. So the original mass, we already have a number in place there, right? T is the time in weeks. We're calculating time as weeks, not days, like in number 1, and K is a constant. So that helps us out. K is a constant. It's not another variable. After 3 weeks, his mass is 97 kilograms. So I have another kind of like a coordinate point there, right? After this much time, his mass is 97 kilograms. Determine the value of K, since we said it's a constant, to 4 decimal places. So here we have our original equation. We basically want to plug in what we know, right? So let's see here. So our W naught is 102, and it gives us another value that when T is 3 on the 3 weeks, it is in weeks, time is in weeks. When T is 3, my W is equal to 97 kilograms, right? And mass is in kilograms. So then if this was my equation, I'm just going to write it out again just to put the numbers right underneath it. W naught E to the exponent KT. My W, when it's 97, and my original weight is 102, E K times 3, right? Because when the time was 3, the weight was 97 kilograms. The original W naught was 102. That's okay to put it in that way. And then it's basically solved for K, because that's my only variable left. And then I'll have my constant. So I could rewrite that as 97. We want to divide by 102, right? Divided by 102. And at the same time, I'm going to make that just 3K, because we're used to the number being in front. Okay. So I have 97 divided by 102 equaling base of E to the exponent 3K. So I have a power. I have a power with a base of E. So how do I go about solving for K? So I can convert to natural logarithmic form, or I can take the ln of both sides. So if I convert it to natural logarithmic form, right? Natural log is just taking the ln. So if I were to take the ln of the left side, the ln of the right side, the good thing is, what I like about this is that the ln of E cancels out, right? So when the ln of E cancels out, I still have everything on the left-hand side. The ln of 97 over 102, which could be just a constant. I can plug that into the calculator, right? Equaling 3K. So then to get K by itself, I would just do the same thing. The ln of 97 divided by 102, and then just to change the color here, right? Divide by 3 to get k by itself and divide that by 3. So k is going to be equal to, roughly, I'm going to get more than 4 decimals. So just take the ln of 97 over 102, that numerator divided by 3, and you should get a value of negative 0.001 and round to 4 decimal places. So 0.168 I have. So that would be my k value. Okay, so moving down to B, after 10 weeks on the diet, what is Joe's mass going to be to the nearest kilogram? Just changing colors here. So after 10 weeks on the diet, so 10 weeks, the 10 is my time, so T equaling 10. My K is a constant, so I can use that number all the time, right? So if K is a constant, K in this formula is going to be from now on negative 0.0168, and just make sure that you've got that written down properly. And so plug that into my formula. So my formula is W equals, it's always W naught. W naught is always 102. 102 multiplied by E, and then these two multiplied by each other, right? So let's say negative 0.0168 multiplied by 10, or you could have the 10 first, it doesn't matter. And these are all numbers, right? E is 2.72, but don't use that. Use the actual value of E. Multiply this first, right? Which if your calculator is where you have to get the number first and then set it equal to E, that actually works out easier because then you can multiply these together and get a negative value. Place it to the exponent of the base of E and then multiply by 102, and you should get roughly, now it says to the nearest kilogram, so to the nearest whole number, you should get roughly, just put the dot on top there, 86. And the mass is in kilograms anyways, so we have the answer of 86 kilograms. And just to go, I'm just looking at my notes here. The original question, it just said, figure out what the mass is to the nearest kilogram. There was no rate given to us, right? So that also helped us to know that when it asked for the mass to the nearest kilogram, I'm just going back to the original equation, just to mention that. I didn't mention that before. Because I'm looking ahead at C, where it's talking about a rate, right? So determine the rate at which he will be losing weight at that 10 weeks, after 10 weeks, to the nearest kilogram per week now. So now that I'm looking at rate, I'm looking at the rate at the 10-week mark, which we already figured out part of that in B, right? So because I'm looking at a rate, I'm looking at the derivative, which I haven't done yet. So my original equation, right, is W equals, because W is varying, but 102, the W naught does not vary. That's always my initial value. There's E, and I have a constant K, but T also varies. So W and T are varying, right? So I can put my K, negative 0.0168 to the multiplied by T. There's my, I want to say new equation, but my original equation with all the information I have now. So we have a constant multiplied by a base of E. So we're going to do the constant multiple rule to get the derivative. Constant multiple rule. So the derivative is to leave the constant alone. Do the derivative with base of E is just to copy out the way it is, right? E to the exponent negative 0.0168t, and then multiplied by the derivative of the exponent. So with respect to t is just the numerical value of negative 0.0168. Okay. And then I want to evaluate that. I could put that in front and multiply it by the 102 right away. And then I want to evaluate that, now that I only have one variable, for t equaling 10. And then I will get the weight, the nearest kilogram per week. So the derivative is equal to 102 multiplied by E, negative 0.0168 times 10 multiplied by the negative 0.0168. to the nearest, it says to the nearest kilogram per week. So I guess you would get a value of like -1. So I might write down like, I mean, if it says nearest kilogram per week, obviously write it down that way for a test. It would just be -1. But just to give a couple, just to show you in the video, with I have -1 point, let's say 45 is my rate. He's losing weight at a rate of -1.45 kilograms per week, right? So kind of like pounds per week at the 10-week mark. So as he's getting beyond the 10-week mark, that was the latest rate that he had. Okay, so for D again, I think I'll need a little bit more room, but I'll explain it first. If his target mass, so his goal weight is 75 kilograms, how long should Joe's father stay on the diet? So how long means we need to solve for T, right? We want to solve for T. And it says if the target mass, so again, it's giving us a mass, not a rate. So because it's giving us a mass, we want to go back to the original equation or the original function. Okay, so I just have that down there. We will move this up. So write out my original, oops, don't have my pen. Write out my original equation. It's always 102, it's always E, and it's always the constant K. -0.0168 times T. And then what did we say? It's asking us to solve for how long, so to solve for T. So the only other variable is W. If the target mass, the future mass would be 75, we put 75 over there then, right? Equals 102 E -0.0168 T, and then solve for T, which is up as an exponent. So again, the first thing I can do, like I did in the previous question, was divide by 102, let's say on both sides. So then I have 75 over 102, just to show base of E, -0.0168 T. And again, we already said solve for T, but I don't have it down there anymore. So to solve for T, like I did in the previous question, changing it to the natural log, or getting natural log is getting the ln of both sides, right? I found easier. You can do it different ways, but if you get the ln of 75 over 102 and taking the ln of the right-hand side, what I like is that it just cancels this out. So I'm left, to me, it's an easier way to solve for T. So then I've got the ln of 75 over 102, which I can just plug that into the calculator, right, is equal to, that's now no longer an exponent. And then if I divide by, don't forget it's -0.0168, cross out, divide this answer as the numerator by -0.0168. Make sure you're doing this on your calculator so you know what the answer is and not just copying down what mine is. So try it right now. The ln of 75 divided by 102 as a numerator, then divide that by -0.0168, and you've maybe never used these buttons all together on your calculator in this form. So just make sure that you're getting how long should his father stay in the diet. It doesn't really give us what to round to here. So again, I have approximately 18.3. So, you should put your therefore statement, right? Therefore, Joe's father should stay on the diet for, just over 18 weeks, or about 18 weeks. Okay, and last question, I believe, E. I might actually be able to fit it right in there. So I'm looking, I don't have a lot written down for it. So let's see. At what rate, there we've got our key hint word there. At what rate will he be losing mass when he reaches his target weight? So at the 18-week mark, 18.3 week mark, what's that rate going to be comparing? It doesn't ask us to, but kind of comparing it to the rate that we had above when he was at the 10-week mark, right? To the nearest kilogram per week. So again, we can round to the whole number of kilogram. So because it's a rate, we're going to be using our derivative. We already have our derivative function written from C. I'm just taking a look, so let's write that out. 102 e to the negative 0.0168t multiplied by negative 0.0168, right? That was the derivative. And just solve for my variable time. You could put 18, but might as well be more accurate and put the 18.3 since it didn't really say what to round to in D. So 18.3, plug that in right here, multiply it by negative 0.0168 as an exponent on a base of E, multiply it by 102 or multiply it by that and then 102. I'll plug that in here, just the 18.3, but you go ahead and start plugging it into the calculator. 0.0168. Show me that the T is now 18.3. And I would say after this step, you can just go right to showing me what the final answer would be. So again, the derivative. I have roughly negative 1.3. And again, kilogram per week. But again, we're not answering, it says to the nearest kilogram per week. So that would just be negative 1 kilograms per week. So the reason why I put the decimals for E, so my answer in C, just to kind of show you the rate was negative 1.45. But if it told us to round, it did to the nearest kilogram per week. That would just be negative 1, right? Kilogram per week. And here in E, we have negative 1.3. But again, to the whole number, to the nearest kilogram per week would still be negative 1 kilogram per week. So, I mean, that is what I'm asking you, or the sheet is asking you to do, then technically your answers would look the same. But I was just showing that technically this rate is a little bit slower than it would be in C, right? So this is the rate at 18 weeks, right? And then we have the rate at, over here was at 10 weeks, I'm just saying, just to compare. So also that is pretty typical when you're losing weight. You'll start out losing weight more rapidly, right? Because there's more weight to lose. And then as you're losing the weight, it obviously slows down. So this kind of coincides with kind of realistically what would happen